Alright, hello everyone. Let's hope you can hear me. Looks like you can. We're going to be doing problem 49 in chapter 10. We're going to be doing four chapter 10 problems, and then we're going to try to do 4 of each and post them on YouTube. I think that's a good idea. So, and then 4 times 4, which is 16 problems total for you guys. So yeah, for this problem, we're going to do for this chapter, we're going to do problem 49. So yeah, let's go ahead and read it. A wind turbine is rotating counterclockwise at 0.5 revolutions per second and slows to a stop in 10 seconds. Its blades are 20 meters in length. A. What is the angular acceleration of the turbine? B. What is the centripetal acceleration of the tip of the blades at t equals 0 seconds? And then part C, what is the magnitude and direction of the total linear acceleration of the tip of the blade that lies along the positive x-axis at t equals 0 seconds? So let's go ahead and get started with part A. Firstly though, let's go ahead and write down the variables that we know. So we know the length, the blade's length. Let's see. So we know that each blade has a length of 20 meters, so we'll say R is 20. And it has an initial, let's see, rotating counterclockwise. Yeah, so it has an initial omega of 0.5 revolutions per second. And we can actually use a conversion factor here. We can multiply by 2 pi, so 2 pi radians, so rads for the units. And then there's 2 pi radians and 1 revolution, so we write revolution in the denominator. So now these units cancel, and we're left with radians over seconds. So let's go ahead and put this in our calculator. But you can probably tell by now it's going to be pi radians per second. Right, because we know half of 2 is 1. So we have our initial omega, and we know that the omega goes to 0. So let's also write our omega final. We know this is 0 because it says and slows to a stop in 10 seconds. So we also are given a time, 10 seconds. Alright, so part A says, what is the angular acceleration of the turbine? Well, angular acceleration, if we want to find alpha, we can look to our formula sheet, but we should remember that alpha equals r times a, and this a is your centripetal, let's see, this a, tangential, okay, yeah. Ooh, sorry. Wow, I can't believe I didn't remember that. So it's the other way around. If you wanted to get alpha, it would be your tangential acceleration. So like the acceleration you apply tangential to the direction you're rotating. So if you're rotating like this, tangential force would come in this way, tangent, and it would speed up the rotation, increase your omega. So yeah, if you want to get alpha, it would be your tangential acceleration divided by r. And yeah, it's saying what is your angular acceleration, so we're going to have to find alpha. And to do that, we need to get tangential acceleration. Oh, okay, we can actually use, to get alpha, we can actually use this equation right here. Because we're given a time, we're given an initial omega, and we're given a final omega. So we can go ahead and do that. This equation is still valid, but we're not going to need it for this problem. So now we can just go ahead and set up that equation. So let's see, it was omega final equals omega initial plus alpha times time. So we want to isolate alpha, right, because that's what we're finding. So we can subtract omega final by omega initial. So subtract omega initial on both sides, and then we can divide by t on both sides as well. And this will give us an equation to find alpha. So yeah, we can just plug everything in because we already have all the known variables. So we know our omega final is pi radians per second. So pi radians per second. We're gonna leave out the units for now. And sorry, this is our initial. So our final is 0, and then we're gonna divide by 10 seconds. So it's negative pi divided by 10. And if we know the units for pi, the most I know is like 4 or 5, so 3.314159. I think that's valid. Yeah, okay. So yeah, that's and this is negative. So yeah, this is our alpha, and we can express it in scientific notation if we want. 10 to the negative 1, but yeah. So this is our alpha. So that's part A done. The angular acceleration, yep. So now what we want to do is find the centripetal acceleration of the tip of the blades at t equals 0. So that's saying, hey, these turbines, they're going at a maximal speed at t equals 0. So what is the centripetal acceleration acting on them at t equals 0? And if you go to our formula sheet, like always, we'll see that centripetal acceleration is right here and also right here. We can use either one. I prefer to use the angular equation. You're completely free to change this and get the v and then put it in here, find it that way, but that's just more work, obviously, because we're already given omega anyway. So yeah, let's go ahead and use that equation. So find, I should kind of try and label my stuff, but so find a sub c. That's what we want to do next. So if we look at our equation, a sub c equals r omega squared. And it's saying at t equals 0, so that's the initial omega. So that's pi radians per second. So you can just write pi squared. And then our radius was 20. Right. This blade's 20 meters in length. So 20. For the turbine itself, I'm kind of imagining something like this. Because it's not really asking us about a moment of inertia, but yeah, I guess if it has length 20. But anyways, this is 20 times pi squared. So our centripetal acceleration, we put that in our calculator. Looks like it's going to be 1.97, I guess I'll add one more sig fig, 4 times 10 to the 2 meters per second squared. And remember, centripetal acceleration is the inward force that goes to the center. So the center of rotation is the direction of your centripetal acceleration. So yeah. So that's part A and B done. Let me just box these so we know the answers. So let's go ahead and move on. And I'm also going to just label them real quick. So this is part B. And this right here is all part A. So now we're going to move on to part C. And let's see. So part C says, what is the magnitude and direction of the total linear acceleration of the tip of the blade that lies along the positive x-axis at t equals 0? So, okay, after a little bit of pondering, what we need to understand is that a sub t and a sub c can represent the x component and the y component of a rotating body. So let's say we have a little object here, maybe a baseball tied to some rope or something, I don't know. It's going to have a tangential acceleration. Let's say it's increasing in angular velocity. It's going to have a tangential acceleration, but it's also going to have a centripetal acceleration that keeps it in this rotation here. So it turns out you can measure these magnitudes right here. So this would be, I mean, with this orientation it's kind of awkward, but let's say we rotate it like this. Man, that circle sucks, but just try that again. Okay, let's say rotate it like this, and now we can kind of see how if this is the a sub t right here, and this is the a sub c, you can kind of see how this is the x component, this is the y component. So that's how you can treat these accelerations. So in part C, it's asking what is the magnitude and direction of the total linear acceleration. So linear acceleration just is an umbrella term that encompasses both of these variables. So both these variables would be considered linear acceleration, right? Because then you would have angular acceleration, that would be alpha. So yeah, that's the gist of what you should know, so you don't fall into pondering like I did. But yeah, so what we need to do is treat these like x and y components and find the total magnitude of the acceleration, the linear acceleration. And the way we can do that is we can draw a little right triangle here, and this we can say this hypotenuse, let's say c, equals that total magnitude. So let's go ahead and write out the Pythagorean theorem. So a squared a squared plus b squared equals c squared. And if we want c, that total linear acceleration, you can square root both sides. So a squared plus b squared. And yeah, we can find out what that total linear acceleration is. So let's go ahead and plug in the values. So let's just go ahead and say a is the tangential acceleration. But let's actually go ahead and solve for tangential acceleration first. We already have our centripetal acceleration, and we have alpha. So if we go to our formula sheet, we'll see that tangential acceleration equals r times alpha. So that's pretty easy to remember. So let's go ahead and do that. I'm going to go ahead and get that out of the way. And yeah, this is what's going on in the problem itself, because it's saying it's going counterclockwise, if you can see that. So we're told a direction, and that direction is counterclockwise, which is negative when we're talking about rotation. Alright, so let's go ahead and solve for a sub t. So yeah, all we have to do is multiply r times alpha. And we have alpha here, and r is 20. So 20 times, what is it, negative 0.314. Yeah. So 20 times negative 0.314, and we get negative 6.28 meters per second squared. Not theta, not radians per second squared, because it's linear. So yeah, we have all the variables we need. We have the y component of the linear acceleration, and now we have the x component of the linear acceleration. So now, yeah, we just plug in the values like we said we are going to do. So I'm going to use a for tangential acceleration. Really doesn't matter, of course. So yeah, let's plug that in. And then b would be our centripetal acceleration. That was a larger number. So if I were to draw these vectors to scale, the centripetal acceleration would be much longer. So yeah. Squared and square root both these values. And so yeah, we can plug this in our calculator and see what we get. So I got an answer. So our C here, we can actually go ahead and change C to just be like total, like sum of A, I guess. I don't know. That's probably not a good idea. Let's just say C. So C equals 1.97 times 10 to the 2. So it roughly equals the same, has roughly equal the same magnitude as this. Actually, let me just add one more sig fig because there is supposed to be a difference. And I kind of lowered the precision of that by accident. So yeah, we're going to add a 5 there. And then times 10 to the 2. So that is our magnitude. Now we need to find a direction. And if we remember from the beginning of the semester, we have to find a direction by using arctangent. So if we do arctan of y over x, this gives us the angle, so theta. So that gives us our angle. So we said tangential was our x and centripetal was our y, so let's go ahead and do that. Sorry. So 0.314, as I keep remembering, yeah. And then divided by 197.4. Yep. So yeah, if you plug this in your calculator, pretty sure it was when our x is negative. We had to add 180, but it's not, so we should be okay there. And let's go ahead and calculate this and see what we get. Ooh, wait, let me just be careful here. Ooh, yeah, sorry, I put in alpha. My bad. So this is not the correct value, sorry. We just calculated the tangential acceleration. It was negative 6.28. Yeah, sorry about that. So yeah, let's go ahead and plug that in. Okay, so let's try this again. Ooh, okay, I was wondering why I was getting a weird answer, but it was actually because my calculator is in radians. So just make sure your calculator is in degrees. Actually, no, it can be in radians. Just multiply by 180 divided by pi. And that'll make it in degrees. So yeah, and if you do that, you should get negative 0.182 degrees. And the negative states that it's in the counterclockwise direction. So pretty sure on the exam you can just say 1.28 degrees counterclockwise or something like that. That should be okay. So yeah, let me just go ahead and add the magnitude with that. So we got 1.975 times 10 to the 2 meters per second. And then let's go ahead and get this over here. I guess it's fine. It's fine. So yeah, this is our answer for part C. So if you enjoyed this video or found it helpful, make sure to hit the like button and subscribe. And we're going to keep doing these questions. I'm going to just do them sequentially. So the next one we're going to do is 51, then 56, and then lastly 71 for this chapter. So yeah, thank you so much for watching, and I'll see you in the next one.